Okay, guys, it's now 7:05. I think you guys have been waiting quite a while. So yeah, without further ado, let's start now. So welcome to the first workshop of the Deep Learning Week series. And this is the first workshop on HML. And together with my friend over here, Yong Hao, my name is Philip, and we are going to help deliver this workshop to you. So here's a picture of us. Okay, bye-bye. Okay, so MLDA's mission, we actually come from a student society or club called MLDA, Machine Learning and Data Analytics Lab at NTU EEE. So this is a student-initiated club or society, which helps to provide an integrated platform for EEE and IM students to implement machine learning and data science and AI, as well as facilitate connections with the industry. So in terms of the events we do support students in the form of FYP or design innovation project you're going to take in year 3. And also we have some Eureka projects also, because we do have a lot of GPUs over here that are used by the students to help run their project in that sense. So some of the events that we do is holding workshops like this. We also have our flagship event, the Deep Learning Week, which is currently now. And we also have many industry projects with our various industry partners like NVIDIA, Shopee, etc. So we are very active in this field in a way. Okay, so that's all about MLDA. So before we start, maybe I can play a video. Please let me know if there's no sound.
Devices are becoming smarter and smarter, and this is boosting many industries. The combination of IoT and machine learning creates opportunities to increase efficiency or save costs. At the same time, however, technical challenges must be overcome. For example, we make freight trains smart. Each wagon is equipped with an energy-autonomous IoT device and various sensors, for example, to measure vibrations and position. Machine learning is used to analyze the collected data to detect impacts in real time. This means that an alarm message is sent immediately if a wagon is damaged, for example, due to improper loading. The challenge is to run the machine learning model directly on the microcontroller of the IoT device and not in the cloud. Why is this necessary? Because transmitting the required data is too expensive and there is not enough power available to do so. We get around this by combining different types of skills, which is known as Edge ML. Thus, in the event of actual damage, just one message is sent. Customers can use our end-to-end IoT solution to detect collisions and potential damage in real time and make warranty claims in a timely manner. This is how we make digitalization happen.
Okay, so if you like to check out the video, later we will send the slides and you can click on the title on the top yourself. So yeah, a bit about, this is basically what we're going to cover today, about HML. And the reason why it's so important nowadays is because, next. Okay, so before that, we'll talk about the workshop outline. You'll divide it into 2 main parts, which is the theory part, and why this trend has so-called hit on. And later, we actually have some demo sessions with a web tool that we will use. And also, you can even use your phone later as a hands-on at the end of the session. So do stay tuned for that. Okay, so first of all, we come to HML, which is stands for Edge Machine Learning. So what is HML exactly, and why is it becoming so prevalent nowadays? Okay, so we are actually shifting to a data-centric world. If you look at the number of job postings for data scientists, data analysts, machine learning engineer, you can see they are indeed rising. Just do a quick Google trend, you can find this kind of data. In some estimates, we generate 145 trillion MB per day, and I think this is going to keep climbing more and more. And if you are talking about company-wise, where in the end we are mostly going to go, they are mostly in the midst of digitalization. So they are definitely using a lot of data to help improve their business and product and service. So they can improve it in terms of efficiency wise, or make something cost less, or then you will generate more. It will be win-win for the business and also for the customer itself, because they can bring the lower cost to the customer also. So it's win-win. Okay, yeah. Then here's if you do a quick Google search on the best jobs, you can find software-based jobs and also data scientists, like I said earlier, and data engineer at the top. So traditionally, a lot of the computing is done in the cloud, where if you heard of AWS, Amazon Web Services, or even Google, they have a lot of data centers scattered throughout the world, and most of the computations actually happen there. So like when you're streaming Netflix, all your data is actually streamed from a server in the cloud, and then it gets to your device. But what edge computing or edge ML hopes to provide is removing this offload from the cloud, coming down to the individual devices. So like your mobile phones, in the case of an autonomous vehicle, is the car itself, or you can have even smart cameras which can do some detection on the webcam or the camera itself. So that's the idea about edge. Is bringing. That's why if you're looking at the graph, if you studied nodes and graph theory before, the edge is the end part. So this is what they meant by edge. Okay, yeah. So here is some samples of edge ML devices that particularly we cover today. So even your watch, if it has some smart capability features, it also is considered edge device. As anything that considers that contains the microchip or something, yeah, you can see that, and many more of this. Okay, so the idea about if you have a look at this last time, these microcontrollers, you can imagine them in even your aircon also. So typically in your aircon, there will be a temperature sensor inside. So this temperature, let's say you set it to 24 degrees, it will detect the environment, and it will check, oh, is it 24 degrees or higher? If it's higher, then perhaps the wind power will increase, and it will cool the room down at a faster rate in that sense. So in this case, it's more of a rule-based. But what happens when you bring AI into these edge devices is actually, they are not so rule-based, but they depend on a lot of sensors. So you can imagine like an autonomous vehicle. You can take in your camera input sensor, you can take in your LiDAR data. You can take a lot of data together, you fuse it together, and it becomes sort of like probability-based already. So what is the probability of a human being in front of me? And then after that, you decide the necessary actions to based on the probability that you decided. Yeah. So there's one startup in the US also, they having a ring that can detect the health points of their firefighters, because they find that some firefighters, they have a heat stroke after fighting the fires. So this kind of data can send live data back to the server, and they can do analysis on it and actually predict whether predict in the future, like if I spend fighting this fire 5 minutes more, etc., will it be bad or harmful to my health in that sense? Yeah. So we come to the benefits of why edge computing compared to the cloud. So if you cut off the network, that means you don't need to connect to any internet for cloud. Then you have resilience against connectivity issues, because in many third world countries, they are still having places where there's slow or no internet connection. So you can imagine one case is like your Google Translate. It needs the cloud, but you can also download offline data so that you can, let's say you go to some place like Korea, you can just do your translation just on the spot with your phone, offline, no data. Okay, and because there's no latency in transmitting data over the internet, you will have lower latency also. So your response time will be faster in this kind. And if you're talking about the cost, upfront, if you are designing a lot of embedded devices or chips at one go, it can be cheaper in the long term also. So you design maybe like 1 million units and you just purchase them at a cheap price. So you will save cost compared to like you have to rent a cloud computing resource or etc. And long-term wise also, yeah, in that sense, the energy requirements will be shifted to the user itself, because will be computed on the user end instead of the company for footing the cost. And yeah, you don't have to pay for so much network bandwidth with cloud because all these are reduced as well. Okay, and I think one important thing about edge computing is the next one, which is actually data privacy and security. So if you're talking about like Google, they love to collect a lot of data to train their models, but they have to make a distinction between some data that is very personalized and should be only kept locally. So if you look at the headline down here, there's a Gboard, Google's Android keyboard, which basically if you used it before, you can if you have typed enough, it will predict the next word that you're going to type. And actually, sometimes its accuracy is very good, actually. So this kind of data, especially if you're typing passwords or emails, you wouldn't want this kind of data to be sent through the cloud and for data to keep. So by doing the inference of the machine learning, by predicting the keywords on your device itself, you eliminate this idea of sending the data on the cloud. So this is the paper about the mobile keyboard prediction, the Gboard. If you're interested, you can take a look at this paper here. But what I want to highlight is this. This we will discuss later. So is we need to reduce the parameter set size, because what happens on the phone is, on the phone for this case, is it has much less computing power compared to a computer. So you need to do some adjustments to make sure your model still runs smoothly and it won't affect the user experience in that sense. And also, since this is a Google paper, it of course uses Google's own product, which is TensorFlow Lite. And this is one of some technology that is helping to bring deep learning models down to the edge, to the microcontroller level, to the mobile phone level. Yeah. Okay, yeah, talking about Industry 4.0 shifts, NVIDIA also just introduced like this on-device GPU in security cameras for local detection. So you can imagine if you are sending video data over the internet, this actually will take up a huge bandwidth, because you are sending 4K data, let's say, then one camera is fine. But 2 cameras, 3 cameras, if you are having an entire campus of this kind of video, the computing end side will be kind of heavy in that sense. But if you're able to do like naive detections, detect there's a human there, or track the human within the camera itself, because you have the suitable hardware for it, then this kind of applications will be better, because you don't have to send, number one, your bandwidth again. And then you have also just local inference is faster. You don't have the time delay. You don't have to deal with network. So again comes back to the points that we discussed earlier. Okay, and also in manufacturing industry, you have something that's rising called predictive maintenance, where it's you use data to kind of predict whether a machine is going to fail or not. So normally people do reactive, like, oh, something spoiled, then you call an electrician or plumber or whatever, or you can do scheduled maintenance, like sometimes NTU does server maintenance for their thing to push updates, or you can sometimes do proactive. But now people are also doing predictive, because there's much more data. You can install a lot of sensors throughout your whole manufacturing pipeline, and you can use it to predict whether the machine is going to fail in maybe 3 months time and 2 months time. So if you are able to predict, you're able to so-called slot well also, then in some sense there's no downtime also in your company, or the downtime is reduced in that sense. Yeah, and this is some of the AI chip architectures that's going up, and most of the one is actually attributed to the mobile phones, because now almost everyone has a mobile phone. If you want to go out nowadays also to have trace together, you need to scan a QR code. Yeah, so mobile phone is a definite thing nowadays. Yeah, you can see it's rising, and some companies are definitely catching on to this also. There are a lot of partners. There are semiconductor companies, CPU processing companies also, that contribute for this development also. And yeah, one thing to note about here is Edge AI, it will not completely replace the cloud. So it will be a complement service. One example is AWS, which is a cloud service provider. It still provide it has a tool here called AWS IoT for the edge if they see the picture. So it's not that edge will completely replace cloud. They will go hand in hand as a complement product or service. And yeah, high demand computational tasks will still need the cloud. So it's not like you can do everything on the edge for now, until maybe there are some more recent developments. And in terms of privacy data, you can learn more about this topic called federated learning, where user data can be first sanitized and grouped together before you upload to the cloud. So you won't have any risk of privacy infringement or anything. And you also don't want to keep this kind of data that might get you in legal troubles also sometimes. Yeah, so with that, the intro, I finish. Then I move on to some special techniques when you're considering HML. So what kind of things we do to the normal machine learning model that makes it able to run on edge. So what are the challenges? Again, I think I mentioned just now already, is because there are low compute resources on the edge device. So, and if your edge device is CPU based, there are no parallelism during the model inference. That means, let's say 3 multiplications can be done in one step if you're using a GPU based kind of thing. But in CPU, these 3 multiplications will have to be split in 3 separate time steps. So you can see it will take a slightly longer time. Yeah, and then coming to why only now, I think you heard of Moore's law before, where the number of transistors on the chip is getting increasing given the size. And some companies like Google and semiconductor companies also, they have invested and they made some specialized chips to be able to run this kind of specific neural network requirements well. So if you have a look at this right over here, there's a 1-cent coin, and if you see some black squares on it, that's actually the Google Edge TPU. So you can see how small that is, and you can be in your phone, you can be anywhere. It's really small. Okay, so before we discuss the techniques, remember these are some further readings if you want to read about it, but you must always check back the model performance to check whether it's doing well. So if, for example, your accuracy originally was 90%, if you do some adjustment and optimization, if it drops down to 89%, you can ask yourself, is it worth the speed up, or is it not really worth it? So if it drops to maybe 60%, and I think that sense the accuracy already takes a very big hit. So perhaps that optimization step brings more harm than actually good. So yeah, the first technique, actually, if you know about neural networks, there are basically a lot of layers. They are joined like this on the left. So they have a lot of connections in between. So one technique is to actually reduce this number of parameters, because if you reduce it, then you essentially don't need to calculate it at all in the edge device. So you can think of let's say this particular, so these lines actually have numbers on them, and they represent the weights of the neuron. So if the neuron is maybe close to 0, like 0.1 or 0.2 like that, and the rest of the other features is actually 5, 6 like that, the weights . So you can think that let's try removing this 0.1 completely. Let's just cut it off, or maybe set it to 0. Then let's see what happens. So if you try it, and you actually see it's that, it doesn't really affect the model much, because it's such a small difference, 0.2 to 0. So why not just remove it completely, and you get a speed up already. Yeah. So that's the idea behind this weight pruning. The second one, which has a more profound impact, is quantization. So if you're looking at a lot of things that we are living actually in an analog world, and the things inside your computer are represented by ones and zeros. They are bits actually. So they're actually sampled at different points using an analog to digital converter. So if you can see this red sine curve on the right here, if you only map it to 8 bits or 8 data, you essentially only get this staircase-like function. So you can see some data is lost, but then we're going to ask ourselves, how much data are we willing to lose? So that's the idea behind it. But the idea is, if you see right here, the left side, normally neural network, the weights, right, are represented in floating point numbers. So that means something like decimal point numbers. So if you look at this, it's quite complicated on the left. I won't go into details on it. So if you're trying to add two numbers, although there are advancements made to floating point processor architectures so that it will be faster, but in the end, right, if you come to the right hand side, if you know simple arithmetic, also you can just do addition on the integer. So basically, what the idea is, a float number is very memory intensive. Number one, if you're using let's say a float 64, you will use 64 bits of data just to represent one single digit number. But if you use an integer 8, if you use 8-bit integer, then you only have 8 bits representing that. And yeah, that's the main speed up idea. So you can see, yeah, basically the idea is integer is more efficient. And you can look at the evaluation time on changing the float 32 to int8 or integer 8. You can see these bars represent the time. So for the float model, it always takes, you can see there's a significant improvement when you change to int8. But again, check back the performance, model performance. If you look on the right here, they look about the same actually. So it's fine to do this step carefully. So yeah, and this actually constitutes most of the speed ups that, or the significant chunk of the model saving actually comes in this step. Yeah. Okay, then the next one is a technique that is not just applied to HML only, but it's applied as a general technique. Because sometimes if you look at machine learning models, they can have a lot of layers. Then which layers are actually very important for the algorithm and which layers are not. So even in a normal GPU case, we can, if we are able to reduce the number of parameters, means we can store less weights, we can store less, use less memory, and also the computation will be faster, you will speed up. So this tweet over here, if you have a look, is just a short summary on what this technique is about. So you prune about 20% of the weights, then you restart again, then you retrain again, then you see whether it does any impact or not. And if it's fine, then good. But if it's not fine, maybe you can revert back, or maybe don't prune 20% of your weights. Not so aggressive, basically. So this is, yeah. And I think, yeah, the final technique is weight clustering. So this helps in memory efficiency, because if I'm able to represent, like, let's say all these green color ones, you see there are 1.7, 1.88, 1.49. If you replace them with just the centroid, -1.26, then you just save these 4 numbers only, and you map the indexes. Because remember just now I said that floating point numbers are much more use up much more memory, whereas this, let's say if it's just an integer 8, you will use just 8 bits. You already have a 4 times saving in memory there. So you just take this like a dictionary or function, you just read out the values, then you can, this is how you can store the weights in an efficient manner. Okay, and yeah, that's all for the general kind of techniques. I then maybe like to discuss one kind of special architecture improvement. So if you look at a convolution, typical convolution, you can see a convolution is basically, I will slide this 9 by 9. You can see the yellow patch, right? I will slide this 9 by 9 grid. Maybe I replay the GIF. Yeah, you will slide along this whole place, and each of these numbers that you see inside will multiply with the number behind it. So that means the number in the red will multiply with the green one behind. And each time I map it like that, I will have 9 multiplications. And if you look on the right hand side, I have 9 places to fill. So just this convolution, this small example alone takes 81 multiplications already. So you can see if you don't kind of address this well, maybe it might take up a lot of unnecessary computations. So one speed up for this is called MobileNet, which introduce a new layer. So basically, you don't need to know the details, but they basically made this convolution separable. So you have some efficiency in computation. You have some computational speedups over there. If you are interested, again, you can look at the paper over here. But I want to highlight this one where the number of million multiplication and addition from the convolution version for 4866, it reduced down to just 569, and you can see the number of parameters it reduced down quite a lot. So this speedup is more beneficial for maybe a CPU environment where you cannot do this convolution in parallel. So if you are able to reduce this 29.3 divided by 4.2, which is around 7 like that, you get a 7 times improvement roughly in also the time inference you can. So yeah, this is one of the methods, and I think there are many other papers or architectures, special things that you can do for this, but it depends on a case-to-case basis. So you typically need to study more and to know more about it if you want to be very specific to the application. Yeah, so with that, I think okay. So with that, I think I will continue on to the next. I will allow Yong Hao to talk about the next part.
All right, thank you, Philip. So yeah, now I'll continue on with the deployment of HML, like the steps and the frameworks. Okay, so yeah, I'll just start off with like edge devices. Okay, these are some of the edge devices that you will use and you will see when we are deploying HML. Okay, so first we have the AI hardware accelerators. Okay, so these are like edge devices that have hardware that can speed up the AI training and all the inferencing and stuff. Because, for example, the Coral SOM is embedded with the Google's Edge TPU, okay, and the NVIDIA Jetson Nano is embedded with a GPU. All right, so these are actually devices that can actually speed run all the AI models and stuff for your edge machine learning. All right, so after that, we have the microcontrollers, which is some of them that are very commonly seen. Okay, so Arduino might be very common for most of you. Okay, the Arduino Nano 33 BLE Sense is special because it is equipped with a lot of different sensors, okay, that can actually help him detect all the edge motions and stuff. So yeah, you can collect a lot of different sensors and actually pump it in, then you can transfer to your cloud and all that. All right, then Arduino Cell is another one that is equipped with a very powerful chip in itself. Yeah, it's kind of different with the rest of the microcontrollers in the aspect that it is very small and the chip is quite powerful. All right. Then after that, we have the microcomputer, okay, which a lot of you are also familiar with. It's the Raspberry Pi 4, okay, which is all the features of the computer that is put on the system on the chip system. Yeah. So essentially, it works like a computer, lah. Okay. Yeah. So these are some of them. Okay. Next. Okay, so what are the common steps to deploy HML? Okay, so yeah, in essence, HML it is almost similar to it is almost similar to a traditional machine learning pipeline or flow. Okay, except that there are some fine tuning steps that you have to do at the end. Okay, so the same thing. So the first step will be the collecting, exploring, and evaluating the data set. Okay, collecting and exploring, you have to do it with your edge device. Okay, so to calibrate it, the data so that it adheres, so that when you train the data on your device, right? Let's say it's trained in a computer, right? The data that you collect is actually calibrated with the edge sensors. All right, so whatever you're training, right, it correlates to what the edge device will detect. All right. So after that, you have to do a feature engineering, okay, which is the digital signal processing. Okay. Why this step is important, okay, is because it will help your model identify features before it goes into the neural network. Okay. So I think some of you are aware that when you are training your machine learning neural network model, right? For example, a CNN, right? The first two steps will be to extract the features, all right? So to extract different features from the data, okay? And if you are doing a feature engineering beforehand, and if the features are already very good, okay, it will leave a lot of load for your neural network model in the sense that the neural network model does not have to be very big for it to identify very strong features before going through like all those text layers to do some computing. Okay, so that is why feature engineering is important. And of course, it also generates a lot of data, as you will see later when we demo. Okay, from just raw data, it can bring out a lot of features for your model. Okay, a lot of useful features. Okay, then after that, we'll be training and evaluating the machine learning model, which is a normal step. All right, and then yeah, the fourth step, okay, will be something related to how what Philip has said just now, which is about the size and efficiency optimization of the model. All right, so yeah, quantization, I believe that you all have heard of it already, okay, from the slides just now. Okay, so this step is important because we have to make it small enough so that it can run smoothly on your edge device, because your edge device might not have computing resources that is as strong and as powerful as your PC, for example, or your GPU. Okay, and then after that will be deployment. Okay, and with all the required operator kernels. Operator kernels is just something that help you run all your code and all that. Okay, so most commonly deployed as C++ library, because a lot of your edge devices, your microcontrollers or all that, they most commonly use C++ libraries. Okay, but of course you can also deploy it into some other forms that is compatible with your edge device. Okay, so that's deployment. All right, so after that, we'll be writing and tuning an application that interprets the model's output and uses it to make decisions. So of course, this is the stage where you utilize your model and get its output and use it for some functions that you would like to write into an application for use in your edge device. For example, predicting something and using the predictions to do something else. All right, so yeah, that is all the 6 steps when you are deploying HML. And yeah, of course, you can see the picture at the right side, right? That there's a cycle, right? So yeah, this is the start of the Asian Pulse marketing, but okay, yeah. So you can see the cycle, right? Yeah, so when you collect a data set, you train your machine algorithms, then you validate, then you embed it on the edge, then you put in the edge device again, then you just collect data again and all that. So it's just a cycle and it just repeat itself. And when it comes to HML. Okay, next. All right. So yeah, so now we'll talk about some common frameworks for TinyML models. So yeah, TinyML in the sense that you just squish everything down. Okay, so TensorFlow Lite is of course quite popular. Okay, I believe most of you might know TensorFlow. Okay, so TensorFlow Lite is just a light version of TensorFlow Lite, literally light. Okay, not heavy. Okay, so yeah, then after that you have Core ML. Okay, that is for Apple library like iOS. Okay, then PyTorch Mobile is Facebook's PyTorch deep learning library, which is coupled with Droid. All right, so these two are like more like customized. So TensorFlow Lite is the more general thing. Okay, next. Okay, so other HML technologies. Okay, these are to facilitate your HML training and deploying and all that. All right, so of course, Onyx is a platform for you to transfer between different types of models. Like, sorry, not models, frameworks. Like for example, if you train something with TensorFlow, you want to convert it to like a TensorFlow Lite, or you want to, the better example would be PyTorch, from PyTorch to TensorFlow Lite, or like whatever things that you think, whatever frameworks that you think would be more suitable for your edge devices. But then initially you can't train it, or it will be difficult to train it in that model directly. Okay, that's why you need Onyx as a platform to switch around. Okay, that's Onyx. Okay, then after that there's a TensorRT, which is for NVIDIA. Okay, like for example, if you want to use it for your NVIDIA Jetson Nano, I think that is the best framework for you to do it. Okay, then OpenVINO, Intel. Okay, if you know about the Intel GPU computing stick, okay, then OpenVINO will be the framework for you to actually do something that, because they are actually optimized for their own hardware. That's why OpenVINO is good for Intel products, like better. All right, then of course there's a TensorFlow.js. Okay, yeah, that is for your more commonly used for your web browsers. Okay, if you want to deploy to your web browsers and all that. Okay, yeah. Okay, so now we'll start the HMPulse train. Okay, so like I said, annotations. Okay, so okay, HMPulse, right? Yeah, is a company that is actually doing something to connect, like make HML more accessible to domain experts. That means that you don't have to be a data scientist to train or build your machine learning models. That is what Edge Impulse is trying to do, making HML more accessible, or ML more accessible to people that are not really specialized in data science. All right. So what it does is it combines AutoML and TinyML. All right. So what is AutoML? Okay. So AutoML is the thing that abstracts the phase between data acquisition and prediction. Okay. What does that mean, right? Is you get your data, right, but then it will actually automatically detect from your data what is the best way to actually train this data. Okay. For example, it will recommend you some neural network models, some parameters, some frameworks, okay, that is actually already there for you to train your data, and you just have to click and let it go, and you come with a model for you to do your predictions. Okay. That is AutoML. So in essence, it skips the step where you have to write your own algorithms step by step. Okay. From after you get your data. Okay. That is AutoML. Okay. So yeah, this step is actually very convenient for people that are not really into like data science and writing code line by line. Okay. Yeah. And then TinyML, okay, is what we have talked about earlier. It's about making your models efficient. Okay. So converting them into a smaller size, okay, and optimizing them so that it runs as efficient or almost on par with the model that is not converted yet. All right. So yeah, in a sense, scaling it down and all that we have mentioned just now, that is TinyML. Okay. So these two are the main subtrees of Edge Impulse. Okay. All right. So when you're using the Edge Impulse framework, right, these three things we believe are some of the most important or most useful aspect of Edge Impulse. Okay. So advanced DSP blocks is actually the the digital signal processing blocks. Okay. So it is very powerful because Edge Impulse is not just for one type of data. It actually has DSP blocks for multiple types of data. Okay. And we'll let you have a look later from the platform. Okay. So yeah, for example, if you just have like simple signal data or motion data, right, you can generate 75 types of data from just one single raw data. Okay, that is the power of the DSP block. Okay, so yeah, you reduce your feature engineering workload for neural network model as mentioned just now. Okay. Yeah. Okay. Yeah. So after that, there's the latency and memory usage estimate. Okay. So what this does is that at the end of your training, right, and when you want to deploy, right, they actually calculate latency and memory usage estimate before you deploy. Okay. So that saves the work for you to like after you deploy, then you have to look at how it works. Okay. How it performs. Then you have to retrain again, then deploy again and all that. Okay. So you don't have to do that because they can actually simulate your hardware performance. Okay, using Raynold. Raynold is some platform for you to like simulate hardware performance with your machine learning model. Okay, so that's why the TensorFlow with the partnership of Raynold can actually is actually present in Edge Impulse. Okay, in their like final step before deployment. Okay, yeah, and then there's a direct compilation to C++ source code. Okay, so this is something that is also very special about Edge Impulse. Okay, their compiler, okay, actually makes use of this TensorFlow like something that is they remove a lot of code from the TensorFlow Lite model. Okay, yeah, so that you don't have to use interpreters. Okay, when you are running your code in your edge device. Okay, so it's direct compilation to C++ source code. Okay, of course, ships data easily into the ROM. Okay, because we flash the model into the hardware. Okay, so once you flash, you don't have to use like internet connection anymore. All right, then your linker knows exactly which operations are being used. Okay, so the linker is actually the one that converts. It's the last mile that converts everything into instructions that can be used by the hardware. Okay, and when you use C++ source code, right, your linker knows which operations are being used and they can cut down on unused codes. Okay, that will actually make it even smaller, okay, and more efficient for your hardware. Okay, so these are the three main things that we want to share about the platform. Okay, next. Right, so yeah, we have a 5 minutes break. And
yeah, we have a 5 minutes break now before we go to the demo and hands-on. In the meantime, please make a Edge Impulse account. It's free, so that you'll be able to do the demo session later because we'll be using it. And do it on PC because we will use both the PC and the mobile phone later. Okay, thank you.
Yeah, so we'll be back at 7:50. All right. All right, yeah. So we'll continue now, yeah? Hopefully all of you are back. Okay. Okay, so for this one, right, okay, we will just demo and let you all feel a walkthrough of what you can do with an edge device, because we believe you all can't follow through without an ESP32 and all the motion sensors. Okay, so yeah. Okay, so gesture recognition on ESP32. Okay, so as you can see here in the picture, we have our ESP32 and we have a LED with 3 colors, like it's an RGB LED. All right, then we have the MPU 6050. Of course, the MPU 6050 is something for the motion, motion detection. Okay, so this is like a cheap version of the Arduino Nano BLE Sense 32. All right, so as usual, you can just like follow some data sheets and then just connect your GPIOs and stuff. Okay, next. So this is how you connect like all Arduinos and their sensors. Okay, next. Oh, it's a demo. Okay, so now we'll demo with like a camera. You want a spotlight? Okay, so but I have to share screen, right? Oh, okay. I'll just share screen. So as you can see here, I have our device. Okay, so before that, let's just go to this. Okay, so if you go into Edge Impulse, right, you see your dashboard here. Okay, so and when I look at my devices, I actually have this. Okay, and okay, how do you have this, right? It's actually something to do with like some Edge Impulse CLI. So if you want to download your Edge Impulse CLI, okay, you have to go to your like command prompt and download your Edge Impulse CLI, and most probably run as an administrator. Okay, so yeah, and and after that, right? If you should be able to download it. Okay, just follow some code. Okay, what's it called again? Yeah, like documentation. Okay, on downloading Edge Impulse. Okay, I will show that already because I downloaded already. Okay, so yeah, after that, right? After you download, right? You can do Edge Impulse. Okay, data forwarder. Okay, so before I run this on my command prompt, okay, I'll have to show you the code that I'm running. Okay, so this is a Visual Studio, and basically it is I'm using Platform IO, which is a substitute for the Arduino IDE, because there are some limitations of the Arduino IDE that actually obstructs some flow of the code. Okay, so if you look at this, right, this looks like a normal Arduino CPP. Sorry, not CPP, like Arduino. Yeah, it's just an Arduino code. Okay, like you have your include libraries. Okay, you have all these. Okay, all these are actually your MPU 6050 code. Okay, setting up the range of your gyrometers, your your accelerometer and your filter bands. Okay, this is the standard MPU 650 code. So what's special is this. Okay, you define your frequency of the data that you want to sample. Okay, and the interval is of course just this. Yeah, you get the period. Okay, so then after that it's just this one. So normally when you loop, right, you don't have to use this one. Okay, millis is just your the time time spent after you started running your code. Okay, and yeah, so every interval, okay, if you run this thing, so this is like the sample rate. All right, so yeah, and you serial.print all this. Okay, so how does the data forwarder work, right? It is actually reading your serial monitor. Okay, so okay, let's say if I run this code, right? I run this code now. Oh wait. I run some code somewhere. Yeah.
The cable issue.
Yes, to yeah. Yeah, so just now we are using some mobile phone charger cable, okay, which doesn't work. So we switch back to the normal Arduino cable. Okay, so now it's uploading. Okay. Okay, so yeah, if you look at your serial monitor now, right? Yeah.
I do.
Yeah, so this is the data that it is uploading, like spitting out. Okay, so if you notice here, I wanted the acceleration in the x-axis, the y-axis, and the z-axis, and also the gyro, which is like the angle or rotation, okay, of x, y, and z. Okay, so after this, right? Okay, I'll terminate this. Okay, so now that the code is uploaded, so I can go to my data forwarder and run this. Okay, so yeah, so now it's actually connected already. Okay, okay, I'm not sure. Oh, okay, yeah. So yeah, thanks Philip for the can. Okay, so yeah, normally if you run this data forwarder, you have to sign in. But since I signed in already, so this is what it shows. Okay, so you directly connect and all that. So yeah, yeah, you have to like normally sign in, then pick your project, and label your data. Okay, actually, wait, should I? I should. Okay, let me just try this. Yeah. So I can pick my project here. Okay, so it will ask you what do you want to label your data as? All right, so like this 6, okay, I know what it is, right? Then I'll just do a CY, this is CY, Z, and gyro X, gyro Y, gyro Z. Okay, yeah, just enter. Yeah, so it's just like that. Okay, so after it's connected, right? So I can go to my this one. Okay, then you can go to the data acquisition. Okay, so here, right, when I say start sampling, right, you actually just sample according to my motion. Like, let's say if I want to sample like up down motion, okay, so take note that we are doing like up down, left right, like circle or an idle. Okay, so let's say I want to do a like a up down. Okay, and I can say just press start sample, and I can just do an upright. Sorry, up down. Okay, then you detect that I'm doing an up down motion. Okay, this is like the Z accelerometer. Okay, so essentially we are collecting data, okay, at the edge, okay, using the edge device. Okay, and yeah, this is data that we have collected beforehand ourselves. Okay, so yeah, after that you can create your impulse and all this. So this is the DSP block power. Okay, so you won't see anything here yet. Okay, but when you go to your spectral features, right? Yeah, this is what it can do. Okay, like you specify all the parameters, like different parameters for your spectral analysis. Okay, and when you generate features, okay, they have a feature explorer itself. Okay, so this is the different features that you extracted from just your simple your gyroscope meter and your accelerometer readings. Okay, so and you can try to work around with this and look at each sample and also see how they are being split in a 3D graph. Okay, so if they are being split very well, right? Okay, so let's say like this one is one category, this one is another category, this one is a third category, and this is all the idle data, right? If you can split very well here, right, then you can expect the model to do really well when you train it. Okay, this is in essence for it to see. And if you want to delete some samples, you can just click here and then go to delete or move them around. Okay, so yeah, this is what the Edge Impulse offers in essence. Okay, then you can train it here, your neural network. Okay, after you train it, you can also do the same, like identify like falsely trained data, and maybe you can move it to your train set or relabel them or whatever. Okay, so later when you do a hands-on demo, you can actually just play around with this as well. Okay, I won't retrain it here. Okay, and yeah, you can do your model testing here as well. Huh? I haven't? Yeah. Okay, yeah. So, okay. All right. So here are the different deployments, okay, that you can deploy. Okay, so for example, we are doing Arduino, so we're deploying it to an Arduino library. All right. So, but in essence, a commonly used library is a C++ library. Okay, then WebAssembly if you want to use for your web browsers, and this is of course for your Jetson Nano. Okay, and when we build our model, right? Oh, okay. Yeah. Okay, so this is the compiler that we are talking about. Okay, just now. All right. So yeah. So in essence, you can see all the latency and all that just here, and with all the data. And so you can see that when you are quantized, that when the model is quantized, right? Okay, your RAM usage is lower, your flash usage is lower, okay, your latency is lower, and all that. Okay, so normally we just select a quantized model. Okay, and yeah. Okay. So there's so many chats.
Yeah, there's one question actually. What kind of model?
Oh,
you can show the custom
okay.
code.
Yeah. Okay. So yeah. I'll show the. Okay. So this is a neural network, right? So just now someone asked, what kind of models do they have, right? So here you can customize it yourself. Okay. So this is like a simple interface. So you can add extra layer and see what layer you want to add. So if you are familiar with machine learning or like deep learning things, right? All the layers or different layers, right? Then you should know what is 1D convolution, 2D convolution, and then your dense layers, your fully connected layers, and then your reshaping, flattening, dropouts. Okay. So this is for the simple interface. So you can just add, for example, if you want to add a dense, and how many layers, like say like 8. I forgot how many there are previously, but multiple of 2. Yeah, so yeah, you can just add and specify that layer. Okay, So okay, if you don't like this interface, right? Like this is too like simple, or it doesn't let you customize, right? Yeah. So you can also do it in your Keras, like code, like legit code. Okay, so if you know TensorFlow, right? So you just import all your TensorFlow things, and then you can specify all the details here. It's the same as your normal code when you are coding your models from scratch in TensorFlow. And okay, there's only one thing that is an issue here, because it might not be able to download weights, okay, from models, from like pre-trained models. Okay, that's one thing that perhaps you can figure out later yourself if you want to. Okay, how do you import weights? Okay, which might be quite challenging. But okay, other than that, you can specify your model however you want. Okay, and yeah, from here. Okay, there's also a IPython notebook. Okay, but that is a bit complicated because when you download the notebook and you do it like offline, right, you don't have access to all the H-Impulse modules or libraries. Okay, that's the thing with this. All right. Yeah. For now, I'll just switch back to okay. So once you deploy, right? Let's say okay. So, oh yeah, one thing I didn't mention is where does the AutoML take place, right? Sorry, the AutoML actually takes place here. This is the AutoML. So let's say I trash this, right? And in the link plot, right? This is actually already like filtered. So these are some of the models that they recommend you, and like especially the star one. So this is what they recommend. That's why I don't have to like click anything, right? Then it just comes out as classification, because regression is not what I want. Anomaly detection is useful. It can be an added thing in your model, okay, because it will let you detect unknown predictions. So when you are training and testing, right, there might be some data that is anomaly or out of all your pre-trained sets, right? Then you can actually train another anomaly detection model and run it. Okay, so let's say I add this. Okay, then I can also add anomaly detection. Okay, so you can train these two together, and then you still get something. Okay, and the anomaly detection will detect alongside with your normal model and tell you which are the anomaly features, and that will just be labeled as anomaly, okay, with a k-means algorithm, okay, which is like a clustering algorithm, like k-means. Okay, so after deployment, right, you will get like a zip file. Okay, this zip file, right, you should open it up, right, you have this folder. Okay, which has all your like source and all this you have like model. Okay, so yeah, in essence, this whole folder, right, you have to use it. So how do you use it? You go back to your this here. Okay, so after forwarding all your data, right, basically you have to run your inference code. Okay. Now, this is one way to do it. Okay, so that I preserve all my platform IO environments here. Okay, yeah, as you see all the libraries. Okay, so for inference, right? Okay, basically, what you have to do is you have to define your frequency interval again. And then, okay, we are using 3 LEDs. Sorry, not 3 LEDs. LED with 3 different colors. So we have to define 3 pins for them. Okay, then, yeah. Okay, here, right, is how you keep track of all your features, okay, that you detected. Okay, so LDC setup and pin mode I'll just not talk about it here. Yeah, then this is your standard code to detect things. Okay, and okay, features and label count. Okay, so yeah, this is just something that we declared earlier. Okay, and then after that, okay, features, IX++, all this is just you keep adding the features into your feature pool, okay, in a sense, and it keeps track of which frame it is it processed already. Okay, that's JSIX plus plus. Okay, then yeah, your signal from buffer and all that, then you run your classifier here. Okay, and yeah, so this is the code that you classify things according to your model. Okay. So basically three things. Upright, upright, up, down, left, right, circle, and idle. Okay. In the case of idle, we'll just make it like no light at all. Okay. And yeah. Okay. So I can upload this. Okay. Yeah. Okay. One thing, the library just now, right? Okay. So yeah, if you see on top, right? Sorry for scrolling a lot. Yeah, this include this one, right? So where does this come from? Okay, so one of the ways that you can bring in your library to Platform.io, okay, yeah, which I discovered, is to go to your Platform.io file in your OS. Okay, then go to the libraries. Then you have to paste. Just now I showed you the folder. You paste the whole folder in. Okay, then after you paste the whole folder in, right? You go to your properties.json and include path. You put in your, okay, I'm not sure. Yeah, this one. Okay, so after you put it here, right, then you can import it as a library, because when we deploy as a Arduino library, right? Yeah, we have to use it like this. It's a header file, and then you remember there's a CVP file as well. So you use a header file to access your CVP file. Okay, so after that we can upload. Okay, sorry guys, I didn't close my sampling code. Let me upload this. Okay, in the meantime, okay, for the quantization aware training, do you mean the quantization during training? Because okay, what I know is that H-Impulse also utilizes the TensorFlow, like the TensorFlow model optimization kit lah, and the TensorFlow. Oh well, yeah, and then this also optimization kit includes the aware, the quantization during training. Okay, but I believe that H-Impulse might be using post training quantization more, because when you look at its training, right? Okay, if you try later, right? Hands-on, right? If you train it, right, then you will see that after it trains everything, then it will actually compile. Then it will transfer it to TensorFlow Lite, then actually just transfer it again with the Eon compiler. Okay, yeah, so we think it's more of a post-training quantization. Yeah. Okay, so okay, now that it's done, right? Yeah, so can look at the. Okay, so yeah. Oh. Okay. Yeah, so you can see that when I do it up, down, I'm not sure if you can see the light. Okay, so the red one is the up, down. Okay, left, right is a green one. Oh my God. Yeah. Yeah, okay. Yeah. And when you do a circle motion, you show a blue one. Okay, why is it flashing blue a lot? Because we actually included the rotation. So when I rotate it a bit, then you detect it as a rotation, a circle as well. Okay. Yeah, so basically this is what you can do on edge devices. So it's a very simple model here. And yeah, what it can run without Wi-Fi because essentially we flash the whole model into the edge device already. Okay, if you want to look at the serial, right, it will look something like this. Yeah, so these are all the detections, like the prediction confidences. Okay, yeah, these are the features. Essentially, all the features and all the DSP is already included. It just runs everything on its own on an edge device. Okay, so yeah, if you want to utilize this for your hackathon, okay, by all means, but you have to have a hardware device. Okay, and yeah. Okay, so okay, that's it for the demo. And I'll pass back to Philip for the collab.
Okay, thank you, Yonghao, for the demo just now. So before we move to the hands-on, I will maybe do a Google Colab demo to actually show how you use how you convert models typically done in TensorFlow and how you convert it to TF-Lite, and also perhaps a sample Python code to use TF-Lite, the model, the binary model itself, to do inference. So yeah. So again, these slides and recording will be shared, okay? So you can quickly take a screenshot, scan this QR code if you want to follow along, but I will be basically going through a pre-run code. So yeah, don't worry about it if you're not, because I just want to show, okay, so I need to see it. Okay, can I see my screen? Okay, good, okay, can see. So if you go to the code, right, it's already pre-run already. This is actually a slightly modified version from the TF-Lite model maker that's available by TensorFlow themselves. So I just added some of my code at the end only. So if you can see a TF-Lite model maker that we install it, this is to convert the model to TF-Lite, basically. It's just another package you just install, that's all. So actually, this one is specific about this use case scenario. So, but basically, what we are trying to do now is just to classify some flowers. So there are 5 types of flowers available. So here's just the downloading step only. Okay, so yeah, I won't run this. Then we do a train test split because we have so much data, we can actually do a 90% train and 10% test. So this is actually the layers that's used in this model is actually using efficient net light. But if you want to change this model spec over here, you can just click these dots and yeah, you can choose whichever kind of model that you like in model spec. Yeah, I think if you guys are interested, you can go through the code yourself. So after this, you just do some training, train for 5 epochs because this is just a demo. And because it's already have transfer learning weights already, it's performing quite well already at the start. So just within 5 epochs, it's already achieved 93% accuracy. So if I do an evaluation on the test set, you also get something like 90% accuracy. Okay, then because this is a TensorFlow-like model maker, you can just do a dot export. But you can find documentations to do TF-Lite exportation using Keras models or even TensorFlow models yourself. I think you can just do a quick Google search on that. So yeah, this is the model export code. And you will find that you have a model.tf-lite that's downloaded to your computer in your downloads. So later I'll discuss actually what you can do with this TF-Lite file. But for now, I will just download some of my own images. I just took 3 random flower pictures from here, example. then some pre-processing code to make it standardized with what the model expects. So yeah, here's is actually, these are the three images that we are loading in. So you can see the first one is a sunflower, second is a rose, and third one is a dandelion. So since the model is about 90% accuracy, so we should expect that later during inference, we should be able to get this kind of predictions. So yeah, so this is just, why did it suddenly move? Okay, yeah, here's the one that I want to highlight, which I added, is actually using a TF-like interpreter. So it is slightly a bit different compared to how you will typically train and evaluate models. So you actually can get input details, and you can, so this is, if you have run the get input details, you will see that there are a lot of so-called metadata and files inside. Over here, blah, blah, blah. But what we can show that's interesting is our input shape. So I just wanted to highlight this shape only. So I will expect a 1, 2, 2, 4, 2, 2, 4, 3. This means that the first one is the number of samples. So this means by default, you can only input one sample by default at the time. Then the width is 224. The height is 224. Then the number of channels or RGB is 3. So if you look at this, earlier on I load 3 pictures, which is actually 3, 224, 2243. I kind of need to change this thing. Okay, so I will change it later, but just highlight the input type. Look, it has changed. Normally weights are in the float format, float 64 or float 32. But you can see for this particular model, it actually shrunk down to the quantization step was done automatically, and you actually get an integer 8 version of this model. Okay, then similarly, the output classes, because we have 5 total number of classes, so you should expect 5 data being 5. That means 1 sample and 5 different classes being the probabilities being predicted. So yeah, this one, nothing. So this is how we actually, so I have an input size of 3 now, my sample size. So I actually have to do something called resize tensor input, where I get this now, that earlier one. Then I put my correct shape that I want. So this is so-called forcing it to do three images at once. But you can imagine if you are just doing it on a phone or microcontroller, normally just 1 sample at a time is good enough, more than enough. Okay, then you have to do allocate tensors. Then you have to set the tensors. This is where you actually set the input inside. So you're actually setting it in now. So just now I resized this particular input details index. Now I need to actually set the value in now. Then I invoke. Invoke is actually the run step in a way. Then yeah, get tensor. So you can think of it like a black box. I need to put it inside, then I need to take it out. So now I need to get out the tensor, get tensor, and I save it in this variable. And if I just do some argument max or something just to get the images, just to get the probabilities out. So if you look at this one, this first one actually corresponds to the sunflower. So this is the index. This daisy, dandelion, roses, sunflower, tulips. So what we typically look in the classification step is the highest number. So in this row, you can see the 1, 2, 3, the 4th one is actually the highest, which corresponds to sunflower. So you earlier on the picture was a sunflower. Yeah, and you actually get the sunflower correct. So I think the best are the rest are just self-explanatory. So you also get the thing. Then also one thing to note is all these numbers, if you add it up, it will become 255. Normally, if you're talking about probability cases, the weights or the softmax, after the softmax, it will be 0 to 1. But because of quantizations, your range of the integer is 0 to 255. So that's why your numbers add up to 255. Okay, yeah, and that's just a short one. So coming back to the slides. So remember I said you have the TF-like file just now. Because TensorFlow Lite is a whole kind of API by itself, you can, there are Python API available for TensorFlow Lite. You can use it in Android. You can use it in Swift, which is the iOS coding language. And you also can use it in C++. So just depending on your use case, you can just use that TF-like model file just now that you obtained earlier. And you can just run it using the API. And do note just now that the TF Lite, right, use default parameters. If I so-called know more of the inside stuff and I want to change a particular parameter to my liking and to make it even more efficient, so I can definitely do it. I think you can have a look at the TensorFlow documents because they are very extensive. It's much better if you know what you're doing. You can look at it lah. Okay, yeah, and then this can be a sample app of what you can build. So yeah, I just took the picture from this place. If you're interested, yeah, you can even test this app out yourself. Yeah, just take a picture and you can do a local inference. So do not, when you're doing local inference, it means that this whole machine learning model or deep learning model is running on the phone itself. It's not even, I mean, you can see a Wi-Fi, but it's not using the internet at all. It's done on the device itself, basically. Yeah. I think, yeah, that's all. And I think with that, we will move on, yes, to our final part of the workshop, which is the hands-on with H-Impulse. So just now, Yonghao went through the demo. We will now use something which is that we can do more since we have a phone. So yeah, what you need is we are going to do a keyword detection. And it's a hands-on. So yeah, you can see this kid getting your hands dirty. So yeah, now is the time to get your hands dirty also. So what you need, right, is I think you have it right beside you: computer, mobile phone, internet, and we're going to predict basically 4 categories of sound. So yes, no, noise, MLDA. Okay. Yeah. Okay. So you can go to H-Impulse already, and you can set a you can create a new project. So for mine, I just call it keyword detection. Okay. Then the first step is since you want to use your phone, you can also use your phone to do the recording of the data actually, or the data acquisition. So over here, I kind of registered mine already. Okay, let me just delete it. Maybe I can register again. So you just head to the devices section. You just connect a new device. Okay, you can upload data anyhow you want, but since I will be doing the evaluation on the phone itself, so I think I would prefer if the microphone also used in the training set is also from the phone. So I can just show this QR code. Don't scan this QR code, please scan your own QR code, okay? Wait, where's my QR code scanner? In the meantime, yeah, it's that simple. Okay. So you can see several things on your phone already. I bet you can see. It just opens a browser. Then you just say, for our case, we will just be collecting audio. So you can head to the Impulse design and do give access to the permission of the phone. Okay, click wrong. Okay, so I have already done some data here actually, but for the sake of the workshop, let us clear everything. Okay, so we can do this live together. Is there anything in the test set? I think I might have some. Yeah, I have some. So using this H-Impulse actually is geared towards people who don't really want to recruit or hire an expert in the field. I mean, you can have some domain knowledge, but you can see the data collection, it doesn't really require very advanced knowledge of this kind of domain. So yeah, you can start recording. Okay, so if you look on your phone now, you can actually label your thing here first. So maybe I first label some, collect some noises training. So you can mute me maybe if you want to have a clearer voice for the next 5 minutes while we take maybe roughly how many is enough? What do you think? We take about 10 seconds of each sample lah. So yes, no, noise, and then for us, I will do MLDA, but you can pick the last word, whatever you want. Okay. Okay. So this is noise. Woo. Noise.
You can sample and split also.
Okay, Yong Hao talked too loud just now, so I'm going to delete his sample. Ooh. Okay, now is the moment where you wish you have friends, okay? Because now recording this alone is a bit cynical. So let's ask your friends to do it. So I'm going to label yes. Okay. Yes. Okay, now it's Yong Hao's turn. He will do the rest.
Yes.
Right.
Okay, so one thing that you can do, right? If you don't want to keep recording separately, right? You can change the length to like 10 seconds. Okay, then after that I can start recording. Right? You can say yes, 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 yes.
Yes, 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 yes. Yes.
Yes, 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 yes. So what this does, right, is you get like a 9-second data. Then you can split the sample. Okay. Then what happens is like, you can try hearing, right? This right? Yes. Okay, this one is useless. Okay. Yes. Okay, yeah, this sounds like yes. Okay, so you can add your segments. Okay, here, then you add one more here. One more here. One more here. Okay, then after that, when you are done, right, you just click. And then this will give you like 8 seconds of data, like, immediately.
Okay, nice.
Okay.
Nice. Okay, see, he did all the work.
Okay.
No, 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 no.
No, 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 no.
No, 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 no. Wow. I think too close.
So, and MLDA now.
Why 31 already? Can you remember record maybe like 2 samples to put in your test set so that you can have a benchmark later to test out. No. 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 MLDA, 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 MLDA. Oh my gosh. MLDA. Okay, you have finished doing this. I don't know whether the others. Are you guys done yet? I think it should be okay, right?
You know, if you guys are done, you
Yeah.
guys can maybe like react with like a thumbs up or something if you want. Yeah, if
Oh yeah, yeah, 1% good. Thumbs up. Okay. We will follow that 1% speed. Okay, good. Okay, so the next part is actually to get DSPs, because okay, there's one girl that asked, is this time just now, is it time series data? So if you look at the raw time series data, it might not be so useful, I would say. But what happens is just now in the impulse design over here, we can actually choose our advanced DSP block. So since this is like a MFCC, right? So we can use like spectrogram, because just now we're doing audio, right? Yeah, you can have a look here, can extract MFCC also. But for me, I just gonna use the spectrogram. Then this one is window size. So let's see how many. Let's say 400. So you can think this one is like one particular recording of 1 second. It takes some window size of 400. Then it shifts it by 50. So maybe now it starts at 50 to 450. Then it shifts it again, now 100 to 500. So it does this until it reaches the 1 second, and it generates like a bunch of features to fit into the spectrogram. Yeah. Then after spectrogram, you can pass it into the classification Keras. So I think, yeah, I'm just going to use default parameters here, and I'm going to generate features. It looks bad.
it's like curious.
Okay, we just leave it a while to run. Okay, yeah, so with that we have run, you can kind of see that it is kind of separated, the MLDA especially, it's very prominent. Yeah, then you have a bunch of cluster points here. So you can have a look at the different visualization layers over here. Yeah, and with that, yeah, we can go to the neural network classifier now. So for here, I'm just going to use a 1D default. Okay.
You don't need your number of epochs.
It's fine. Yeah, it'll be quite fast, the training. Okay, I wish I didn't put 100 epochs. So you can see that the validation test actually scored 0.9231, because if you once you do the spectrogram analysis, right, you're actually extracting. It does most of the heavy lifting of the model. So it extracts very useful features that is able to fit into the model. Then the model is able to use these kind of features to do prediction on actually what are the probabilities, or do regression on the probabilities of a particular voice file being in one particular category. Yeah. So now we're just waiting for it to convert to a model, the optimized model.
If you want to try out the data augmentation feature, right, you can also try to, yeah.
If you want to try data augmentation features, if you're more experienced and you know the more advanced stuff, you can also customize. But again, the best is if you want to just use the Keras expert mode, you can just go here. But I think if you are coming from a deep learning background already, you should be quite familiar with all this. Yeah. Okay, with that, yeah, you can see that the training accuracy just now that we did. Oh, for noise is 100%. Wow. What? There's no MLDA. Where's the MLDA? It's still running. What the? Oh, model training complete. Okay, good. Okay. Okay. Now finally it finished training. And he also finished converting into this float 32 models and integer 8 models. So actually the training step didn't take too long. Normally the conversion step that will take longer. If you just now look at the flower classification also, right? The part here where it says model dot export, right? This one also takes a while to run because he's trying to find the best way to optimize the model. That's why. Okay, yeah. We have, wow, MLDA is good. Okay. So this is roughly the confusion matrix of the validation set. So if you want to train it, you've trained it already, right? So now you can go to your phone. If you notice down there, it says switch to classification mode. You can just click that, tap it, and yeah, you're ready to do classification on it. So what it's doing now, right, is it's downloading all the necessary data to your browser, and after you finish downloading, you can try switching off your Wi-Fi in your phone also. You will still be able to run because you remember that this is a HML. It will not need a Wi-Fi connection to actually infer the moment you finish downloading. Okay. So you can see I'm not talking now. It's okay, it's hard to see. I think you guys can test it on your own phone. If you guys don't talk, right, just leave it there, right? The noise probability should be very high. Yeah, which is the case. If now I try saying those keywords that I just now say, yes, 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 no, 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 yeah. And MLDA, 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 MLDA. Oh, it's very good. This is one. Yeah. So this is just a little taster of how this can be done using H-Impulse. So yeah, I think I'll let you guys try it a little more. You guys can try it after the workshop also. But for now, yeah. If you guys don't mind, could you guys turn on your webcam so that we could take a photo for our publicity purposes lah. Okay, more people. Yeah, we wait. Come on, don't be shy. Okay. think that's all. Okay, so more people still want. Okay, if you want, please on first. Thank you guys for turning on your cam. It's a good thing. You guys can be posted. Our first workshop of deep learning week. Then you see your faces on Instagram. Very good. Okay. You guys smile. Okay, I'm going to take in 5, 4, 3, 2, 1. Okay, give me a second. Yep, okay. Thank you everyone. Wait, don't go first. Wait, we still have something. Okay. So yeah. Then tomorrow and Thursday we also have some more upcoming workshops. Introduction to MATLAB. Am I muted? Oh, sorry. Okay, I didn't share screen. Okay, sorry about that. Okay, yeah, we'll have 2 more workshops coming up this week. Introduction to MATLAB for deep learning. And also, if you want a continuation from this workshop, because we kind of use H-Impulse only, you didn't really get to deep dive in the code. So if you want, on Thursday, there's also a TensorFlow for mobile and IoT devices. And this particular workshop will be more practical and hands-on. So you'll be able to touch more heavy side on the code. And I mean, you'll still touch on like state-of-the-art algorithms and some theory. Yeah. So these are the workshops. If you want to register for them now, you haven't registered for them, you can use your phone and scan the QR code in the meantime. Okay, I'll leave it up for maybe a few seconds. Don't worry if you guys don't have the QR code, you can find it in your MLDA email, or you can check us on our MLDA Instagram and LinkedIn also. Okay. Yep, so with that, we have finished and concluded the workshop. If you have any questions, feel free to ask it in the chat or unmute your mic. And then can you also help us fill a feedback form for this workshop? Maybe you see there's a silent emoji there. Maybe there's something inside. Okay. Thank you everyone for coming. Yeah, you have any?
Okay, yeah. One thing to add, yeah. So you all can actually check the H-Impulse documentation for a lot of like further stuff that they have, right? Because you can find out what are all the features. What does all the feature blocks do in the documentation? So they have a very detailed description of what each parameter does for your data, and they also teach you how to deploy on all different edge devices, including your Raspberry Pi or your web browser using the WebAssembly file, and all other things as well. So there's a long list of devices on the documentation. So okay, for the WebAssembly one, right, you also have to work on how to convert your data from the raw form into the quantization form before you put in. So for example, right, if you look at your,
maybe you go slide.
Yeah, I'll stop yours though.
Yeah. I'll send the feedback link in the chat.
So it's a good page. So here are all the development bots that you can use, and okay, so okay, this is for the Linux one, your SDK, and blocks. Okay, so yeah, if you come here, right, then you actually teach you how to use the WebAssembly file to put in your browser. But then there's one thing that you have to take note, because when you put in your data, right, it will be in you'll be already in the integer form like this. Okay, so if you are doing your audio recognition order, right, this raw feature will be integer. but when you are sampling from a microphone directly, right, you get a lot of floats. So to convert that, right, you need synchronization techniques. So for example, dividing by max in the array and then multiply by the maximum number that you want, like a few thousand. Then you get some raw integers when you round it up to integers. Okay, that is one thing that you have to do before you use this model. And you also have to access all your microphones through your browser with the HTML. Okay, so this is something that you have to take note of. Okay, and besides that, if you want preview data sets for keyword spotting, they have like a few thousand yes, no, noise, and unknown data in their data set. Okay, so if you want to make use of that, you can. Okay, and the noise is like all sorts of noise, like tab or running tab or cars or airport announcements, and all that is all inside this preview data set. Yeah. So do keep a lookout for this documentation if you want to learn more about Edge Impulse or use it more for your other projects.
Yeah, I think about Edge Impulse, when we first look into it, right, it actually is very beginner friendly because you don't need particular domain knowledge and you can already use it as it is. The website also, all that is quite user friendly.